Hi, welcome to the session, Introduction to R. My name is Richard Li. I'm a postdoc associate at Department of Biostatistics at Yale University. So in this lecture, we will start to see actually how we're going to implement some of the methods that we have discussed in this lecture series. The programming language that we'll be using for this lecture series is a statistical programming language called R. So for a lot of you watching this video, you probably have used R before in your own research or work. That is great. If you haven't used R before and you work with data a lot, I would definitely recommend you to at least pick up R and see how it goes. And hopefully by the end of this lecture series, we'll see why it is very good to use R and how impressive it is to use R to do a lot of those tasks. So for this particular lecture, I will start with some of the basic ideas about R. So if you haven't used R before, I'll give you a relatively gentle introduction to the R language. Of course, I won't be able to give a full course of how to use R, but hopefully I'll have enough material so that you won't get lost or get too distracted by the syntax of R when we go through some more complex codes. So I will start with how to use R, the R language. What software we use to run R, what is R package, what are R packages, and some basic data structures in R that we'll be using in this lecture. And then I will spend a little bit more time on visualization. I will show you how to make plots in R, and in particular, I will introduce this package called ggplot2, which basically allows you to break down a more complicated figures into smaller components so you can gradually build up to have more flexible and, frankly, prettier pictures using this idea called graph graphics. And of course, since we're talking about spatial questions, I will also show you how to use maps, how to read maps into R, and how to visualize maps and put data, combine data together with maps. And of course, as the main focus of this lecture series, I will use examples that are basically calculating design-based subnational estimates of under-5 mortality rates using our package Summer as an illustration of some of the concepts that we're discussing in the introduction session to R here. Okay, so why do we want to use R? First of all, of course, R is free, so you don't need to buy a license to use R. You can just go to the website if you haven't downloaded R already. There's a link to the R project website. You can download the software, install on your machine, no matter if you're running Windows or a Mac or on a Linux server. You can pretty much install R on most of the major platforms. And also, R is open source software. It has a large collection of the add-on libraries, or what we call packages in R for data analysis. It has a very large user community and also a community of contributors. So basically, for a lot of the state-of-the-art statistical methods you see in papers, chances are once those methods are out, someone or the authors themselves will turn them into implementable R packages or R codes. So it's a really great way to keep track of and up to date with some of the latest developments in the statistics community as well. And of course, since R has a lot of users right now, if you have questions about R, about the language, it's very easy to just type this question into your browser and Googling it, because with this many people using R right now in the community, chances are you will find answers relatively easily by just Googling it online. Another software that we will be using for this lecture is a software called RStudio. It is something called Integrated Development Environment, or IDE. So it's basically a graphical user interface to programming R. It's also free and then also runs on multiple platforms. So if you need to work on Windows machines at some time, in Mac and other occasions, if you use RStudio, it will give you roughly the same interface. And there's a link to download RStudio, and you can see this from the screenshot here, that it basically breaks your screens into a few panels. So there is an editor panel where you can open your codes, can edit your codes, your code scripts. And then there is a console where you can evaluate your codes. And there is an output panel where your figures are nicely organized over there. Of course, for RStudio is basically a graphical user interface for R. It doesn't change anything, or it doesn't add any new language to the R language itself. So if you use another editor, if you use Terminal or some other IDEs for developing R codes, that's totally fine. It will run the same way as if you're running in RStudio. But we're going to be using RStudio for this presentation because it makes the presentation relatively easy to follow. Okay, so some basic concepts of R. So if you have already downloaded R before, used R before, you probably know this or have discovered by this point that you can use R by just typing the codes into the console. So you can type 1 plus 1, it will give you, it will evaluate this expression and give you result 2 at almost real time. So basically, in that sense, you can consider R as a very fancy calculator. But for anything more complicated than that, you typically need to write a script. So a R script basically contains the codes to perform the analysis. That is what we will do in the demonstration later, that we'll write the R scripts, and from the beginning to the end, we'll go through the whole workflow of a data analysis. So another concept that's probably common to a lot of programming languages is a function. So a function basically has a name, and it takes the inputs and a bunch of specifications from the users, and also, of course, the data. And then it carries out routines and produce outputs. So in R, once you download R for the first time, you'll find that there are already a lot of functions built into R, such as means, sums, so all those relatively simple functions. But for a lot of more specific functions, what you will need is something called a package. So packages are basically a fundamental unit of shareable codes, data, and documentations. So what happens is when people develop new functions, new methods, they can combine those functions and codes and some example data into, put them together into a package, and and you can post a package online, and people can install the package directly to use all those codes. So a lot of the R packages are hosted on this thing called the Comprehensive R Archive Network, or CRAN. So for the package hosted on CRAN, you can install the package relatively easily by this one line of code that says install.packages followed by the package name. And we'll demonstrate that later. You only need to do that once. The first time you install the package, you need to use this line of code, but the next time you only need to load this package into your workspace. So you can just type this library package name to load them. So speaking of workspace, the way we work with R is basically when we start a R session, we'll create something called a workspace, which basically holds all the objects we included. So we can load in data to this workspace. We can create functions. We can create values. We can create intermediate values in our analysis. And of course, the results of analysis, they're all saved in this thing called the workspace. And of course, since we're working with data, we usually need to load a lot of different formats of the data into R. So sometimes our data comes in as a format of the CSV file, Excel spreadsheets, a text file, or sometimes we need to probably load data from other programming languages or softwares like Stata. And R has functions to do all of that. Most of the data formats, there is a particular way to read into R. And we will actually see how we can load in .dat file, or for those who are familiar with Stata, the data files that you will get from the Stata program. And of course, since you need to load in the data, one thing that is typically can be a little bit confusing for new users of R is that you need to know the directory of the data. So basically where your data lives on your computer. So the way we're going to work in this set of lectures is that we're going to specify something called a working directory. So basically what I will do is whenever I create a new R project, I will set the working directory to the folder where most of the things lives in. And then from there, I can put in all the data, scripts, and also I'll save the results in the same folder so that whenever I need to load something, I'll need to specify the directory relative to my working directory. So in that way, you can move the whole folder somewhere else, and you don't need to go in there and change all the directories in your codes. And we'll see what it looks like in a couple of minutes. Okay, so visualization. So this is another topic that we'll discuss today and in subsequent lectures as well. So in R, there are a lot of ways to make plots. The simplest thing is probably just like if you want to make a scatter plot of two variables. If you have two vectors x and y, you can simply do plot x and y and give you a scatter plots of those two variables. For simple exploratory purpose, this is great, but as you build on to as you build up your figures and try to make more complicated or more flexible visualizations, sometimes you might find it is harder to use those simple functions because they're not really that flexible internally. So the package that we'll be using for visualization mostly in this lecture is something called ggplot2. So this is our package that basically does a lot of very nice visualizations. And if you have seen codes from ggplot2 before, the first time you see it, it probably looks a little bit intimidating because you need to write a lot more codes than plot xy to just get even a relatively simple visualization. But it turns out that if you get used to the idea of ggplot2, it has a much nicer way to specify more complicated visualization. So the idea behind the ggplot2 is something called the graph graphics. So basically, when you draw the graph, you need to specify a few components, as you will see in our codes a few minutes later. So the least thing you need are those three things in green on these slides. First, you need to specify data. So what is the data you want to plot? And then you need to specify something called aesthetic mapping. What basically says that which variables in the data map to what visual components. Right, so you need to specify what x-axis are, what y-axis are. If you want to use color to encode different categories, which variable corresponds to that categorization. And then you need to specify something called geometric objects, which basically says what kind of plot you want to make. So whether or not you want to make a line plot, dot plot, bar plots, or for maps, whether or not you want to plot the polygons. So later, as you see the codes, you will see sometimes actually, a lot of the times that we will write something like geom underscore say line that basically says that we're going to make a line plot. Okay, so on top of that, of course, you can build on more and more features. You can add in different themes. You can change the scales. You can change the coordinate system. You can change the facets. But the fundamental idea of a ggplot2 is basically that by specifying each of those components, you can have full control of what the plot looks like. And in this lecture, we'll start with relatively simple form where we only specify the first three elements and then gradually build up towards specify more and more and see that the visualization will contain more and more information and also prettier as we specify more themes. Just as an illustration, we'll start from something like what's on the left-hand side here, this relatively simple plot of a line plot or a map, to a more informative visualizations on the right-hand side. And those are the figures that you will be able to create by the end of this lecture. Okay, so as I said before, I'm going to use under-5 mortality rates as an example. So we will use it to demonstrate ideas of how to download and how to install our packages. So we will need a couple packages. We will need Summer to do some of the calculations for calculating U5MR. And then we'll need a package called the survey package to get the design-based estimates. And we also need a package to load the data files from the DHS websites. And we'll go through all of that in a hands-on demonstration in a few minutes. Okay, so basically for this lecture, the learning objectives are twofold. So first, I want to briefly demonstrate some of the features of R. How do we do all those things in R? And then, of course, more to the point of this lecture series, I want to also introduce and get you familiar with how do we calculate child mortality and how do we understand the survey designs. What are the things that we need to do in order to eventually fit the models that will be discussed in the following lectures. Okay, so before we switch to R, I just want to point out that there's websites where we'll host all of the lecture materials, documentations, and if you go on there, there will be a R script accompanying this lecture. There will also be a HTML file where you can go through each of the things that we did with a little bit more explanation there. And of course, if you go to this PDF file, you'll see also there are links to some additional materials for learning R if you're interested, which we won't have time to go through a lot of the details. Okay, so with that, we're going to switch to RStudio. And the screen you're seeing here, this is the RStudio screenshot. You have seen the lecture a couple of minutes ago. The file I'm opening here is not exactly a R script. An R script would look something more like this, where it's completely just all codes. And here, this is something called a R Markdown file. And the reason I'm showing you here is because this file allows me to compile a very nice HTML output, which you can see here. So if you go to the course website, you'll see HTML files and R codes associated with each of these implementation lectures. And from there, you can see we have not only the codes, which are in those gray color trunks, and then also some more explanations in text, as well as if you go down, and when it gets more complicated, there are also outputs and figures all in one HTML file. So it is a good way to keep track of the lecture material and also practice alongside seeing what the expected outputs should be. Okay, so I won't go into too much detail about this R Markdown file. It's not the point of this lecture, but there's a nice website if you want to learn more about how to make reproducible reports. Okay, so let's talk about R. So I'd like to start with a little bit of introduction to some of the basic fundamental data structures in R, which will be used throughout this lecture series. So just in case if you haven't used R before, you see some of the syntax that might seem a little bit weird at first, but once you get used to it, it's quite intuitive. So as you follow along the lecture series, you might be more and more familiar, and hopefully they don't distract you too much from the slides. Okay, so here are some of the basic data structures. The first I want to show you here is something called a vector. So in R, just like a lot of other programming language, we create a new variable when we program, and then we assign values to this new variable. So this notation here, this arrowheads, or you can also use equation sign, basically says that we're going to assign whatever is on the right-hand side to the variable that we created on the left-hand side. So for example, before we go into the vectors, so here the first line of code I wrote is basically saying that we're going to assign this character string that's called hello into this variable called x. So if you type here, okay, so I type x here, and it gave me this character string I just created is called hello. Okay, so in R, the first data structure that's called a vector. So a vector is basically a ordered collection of elements of the same type. So for example, this line of code, it says y equals c 1, 2, 3. The c notation is the syntax in R to create a vector. So you can run this line of codes, and you can see down here that y equals 1, 2, 3. So it's a very easy way to assign a vector of numbers, characters, or a lot of other data structures. So of course, there are also other types of ways you can assign new vectors. For example, this line of codes, which you will also see me using repeatedly in future lectures, that I'm creating a vector called x, and I'm assigning the value 1 to 100 with a column here. And what it does is basically very intuitively creating a vector of length 100, and instead of going through each element and assigning them with a for loop, I'm just creating this sequence of numbers directly. Okay, so that's a vector. And of course, if we have a one-dimensional object, it's a vector, there are higher dimension extensions to it. And in R, the two-dimensional extension of the vector is something called a matrix. So the way we're going to assign a matrix is by using this function called, not surprisingly, matrix. So here I'm assigning a matrix of value 1 to 24. And I'm creating this matrix so that we have 3 rows. So you can also equivalently specify it with 8 columns. It will be the same. And if you look at X, you can see that the numbers 1 to 24 are assigned column by column. So you go from 1 to 3 and then go to the next column. Okay. So how can we make this matrix go the other way around and assign the values row by row? Suppose I don't know how to do that, but I think this seems like an intuitive thing that people might have thought about before. So one way we can find out is by this syntax. It's basically starting with a question mark and then followed by the function name that you want to get help with. So what this does when you implement this line of code, and it will pop out on this side of the screen a documentation of the function that you want to look at. So for example, here for this matrix function, there are a whole bunch of things, starting with the arguments. As you can see this, we specify data, we specify number of rows and rows. There's another argument that's called by row, which is a logical variable. If false, the matrix is filled by columns. If otherwise, it's filled by rows. So this looks exactly like what we want to achieve. So you can go back to this line of code and try it out. So I'm just going to add another argument called by row equals to true. And now I look at my X, and it's exactly as we expected. The elements are assigned row by row. So this is one way that is typically very useful, especially when you work with new functions that you haven't used or not familiar with. You can always just type this question mark followed by the function name and look at the help files. There are the usage arguments, and for most of the functions, there are also examples down below to help you guys through how to specify some of the elements. Okay, so back to our basic data structure. So we look at vectors, matrices, and a higher dimensional extension of a vector is something called an array. For example, this line of code that's creating an array called Y, again with numbers 1 to 24, and then I can specify dimensions. In this case, the first dimension contains 2 elements, and 3 and 4. So basically, you can specify whatever higher dimensional objects. So this is a cube, but you can think about specifying more dimensions as well. Okay, so one nice property about R programming is that a lot of the operations are actually vectorized, especially some of the built-in ones. So what it means is that if you want to calculate, for example, you create a matrix or a vector, you want to calculate for each of the elements its square plus 1. So we created this matrix X before. And this line of code does exactly that. So you can just use a matrix and take its square. And what it means in R is to take the element Y square. And then you can add 1 again to each of those elements. So again, if you check the X here, you can double check that exactly that performs this element Y's operations. So similarly, you can do this for log, exponentiate it, and a few different built-in operators as well. And this is a much faster way to perform simple operations than going through a for loop like you would do in a lot of other languages. Okay, so those are some of the more fundamental type of the data structures. And in all of the vectors, matrices, and arrays, you have to make sure that all the elements are of the same type, because otherwise R will internally force them to have the same types, which is sometimes not what you want. So here we're going to introduce 2 slightly more complicated data structure. The first is called a data frame. So data frame basically looks exactly like a matrix, with the only difference that a data frame allows you to make different columns to have different types of the data. So this is something that you might be thinking about data in your minds when you think about something like Excel spreadsheets. So for this 3 lines of codes, I'm creating a data frame. And I'm creating data frame such that it has 3 columns. So we have a column called ID, a column called name, and a column called color. And in this very simple case, I'm creating this data frame so that the ID column takes 4 values, 1 to 4, and the name takes values A, B, C, D, and the colors take those 4 different colors in vectors. So if you look at your X, and now it looks just like a matrix, but the first column is a number, and then the rest of the columns are other things. Okay. So again, this I don't have a lot of time to go into many of the details about specific data types in R, but I do want to note here that a lot of times some of the data types can be confusing, such as the difference between vectors and the character strings. So there are a lot of great tutorials out there, and here I'm including a link. So if you're looking at an HTML file, you can go to this online book, and it will go through some of the more details about how things like characters, vectors, and numbers are different internally in R. Okay, so the last data structure I want to talk about is a list. So a list is an even more flexible way of specifying a data structure in R. So it basically, literally means a list of things. So it doesn't even need to have the same dimensions or the same number of elements for each of its components. So for example, here I'm creating a list of Y, and the first element I'm calling it apple, and it takes value 1 to 20, so it's a vector. And the second element is called orange, so it's totally different from apple. And here the orange, I'm assigning its value to be this X, or this data frame that we created. So if you look at Y, you can see that it just attached one thing after another as just like a list. So the first thing is apple, the second is orange, and they can be completely different. So this is a very helpful data structure if you write functions, because you might want to return a whole bunch of different things. And it is actually typically how people return in objects when they write functions in R. Okay, so now we have looked at those several different data structures. So one of the things that are very useful, and actually the reason I want to start with data structures, is that a lot of times in R, or when you do any kind of data analysis, you typically want to subset your data either by rows or by the columns, or pick up specific elements. So the way you do that in R, the syntax you need to use depends on what data structure you're using. For example, if you want to subset a vector or matrices, you can do something like this. So here, or a data frame in this particular case. So here, X is a data frame, and I'm specifying row number 1 to 2, so the first and the second rows, and then I leave the column index to be empty. So what it does is that it basically creates a subset of my data frame X, so that it only takes the first and the second rows. So the same syntax can be used for matrices as well. And if it's a one-dimensional object or a vector, then you don't need this comma empty, and it will take the first and second elements in your vector. So of course, you can also subset on both the rows and the columns. So for example, here I'm taking the first and second rows and the second and third column for this data frame X. And a lot of times, a even nicer trick is to specify the rows or the columns not by their indices, but rather by their names. So in this case, I'm taking out the columns in X, which corresponds to the columns with names that are ID and name, respectively. And as you can see down here, I'm just taking out those 2 columns in this data frame. Okay, so finally, this is a little bit different from before, that if you want to subset a list, remember a list is just a list of all different things, you need to use a little bit different syntax. And in R, the syntax to subset a list or to get a particular element of a list is by using this double square brackets. So for example, this y, double square bracket 1 basically means to take out the first elements in this list y. So again, you can use the names to refer to a particular element in the list. For example, you can replace this y by this by the name. So actually the first one is apple, but here I'm using the orange. So I'm taking out the element called orange in this list y, and gives me the data frame that we just created. So another way you will see me using a lot of times in the future lectures is to use this $sign. So this $sign here basically does exactly what this second line here was trying to achieve. So this $sign followed by the name also gives you a particular element in this list, but with the only difference that you don't need to wrap this name with a quotation mark like you do in this using this syntax. Okay, so with that, we'll conclude with some of the basic data structures in R. Of course, there are a whole bunch of different things and a lot of complexities once you go deeper and deeper into learning R. So I hope that if you want to learn R from scratch, definitely check out some of the tutorials at the beginning and also in the lecture slides. And in this lecture, this is all we're going to talk about the fundamentals of R, and then we'll move on to talking about R packages, functions, and some of the specific tasks that we want to implement in this set of lectures. Okay, so moving on to R packages. So as I said before, a lot of the packages are hosted on CRAN, and for those packages, you only need to use this install.packages to grab those files from online and install on your local machine. So some of the packages that we'll be using for this lecture series are ggplot2, as I told you earlier, for visualization. There's this package called rgdale, which we will use to load shapefiles into R so that we can plot the maps and do a lot of other things. There's also the survey package we will be relying on for getting the design-based estimates so that we can take into account the survey weights correctly. There's also the package summer, which of course we will eventually use it a lot to do space-time smoothing and calculate subnational estimates of child mortality in this course. So two additional packages, one I will be using today and another I'll be using later, which are not that essential, but we'll use that to demonstrate some of the points here, are the read data 13, which allows you to read the data file, the .dta file from your computer. And there is a great extra package which we'll use for visualization later. Okay, so if you haven't installed those packages, I will select all of those lines and implement them here. For me, in this presentation, I have already installed them, so I will just skip this step. So another package that will be used a lot is this inla package, which provides a lot of the very basic functionalities that will be used to fit very complicated space-time models. So unfortunately, inla is not hosted on CRAN at this moment. And if you go to the website, the course website, and see in the HTML file, there's a link to the R inla project website, which I'm highlighting here. From there, you can find a lot of documentations and examples, as well as this line of codes, which tells you how to install inla from its websites. Okay, so suppose now we have installed all of those packages. If this is your first time, you take a little bit more time. After that happens, I'm just going to use this library followed by the package name to load the package or to attach the package to my workspace. So you can actually check what packages are installed on your computer and which ones are attached to your workspace. Using this line of code, the code session info, so you can see that I have a lot of packages installed, but only a couple that's attached to this workspace at this moment. Okay. So that's the basics of the packages. The next topic that we'll discuss is how do we load maps. So for this lecture, we won't be plotting this particular map from Kenya in particular, but it will be helpful to go to this website. So there is a DHS spatial data repository, at least as an example, and we are actually going to use this map in later lectures as well. So there's a link to the DHS spatial data repository. From there, you can download something called shapefiles, which basically gives you the spatial polygons that allows you to plot the maps in R. So there, if you go to the website, you can select, it's pretty intuitive, you can select the countries and download their subnational boundaries. And from there, you can it will be a zip file downloaded to your computer. If you unzip it, you will see a bunch of files. Typically for shapefiles, it contains those three files, .shp, shx, and dbf. That each encodes different information of your spatial map or spatial polygons. So for this set of nodes, I have set up my folder structure in a particular way. So that's why we have this line of codes. But for you, if you know where the shapefiles are stored that you just downloaded, in R, you can just use this library rgdel. This attach the rgdel function package to your workspace, and it pops up a bunch of information out there about which version of the things I'm using. And then you can read in the shapefiles using this read OGR function. And you see that it's giving me an error message here because I haven't specified my working directory. So as I said before, I need to either give the exact location of the files, or I can specify the working directory, and then everything will be specified relative to my working directory. So I will set my working directory to the source file location, which is the location I'm saving for this R file. And then I can run this line of codes. And this time it works. It saves my the spatial polygons into this structure, into this variable that's called geo. And you can see here on the right-hand side, there is a geo in the data field, and it is a large spatial data polygon data frame. So one thing you can do to check that you're doing everything right is to just run this plot geo function, and you can see this map being plotted out here. Of course, we will improve upon this map so that essentially it will look much more informative than just the boundaries. Okay, so that's some of the simple concepts that we will be using throughout these lectures and the future ones. So now we're going to go into an actual example where we're calculating the design-based estimates of under-file mortality rates in subnational levels. So in order to do that, first of all, of course, we need the data. We need to get the data somewhere. So for this lecture, I'm going to use this DHS model datasets, which is freely available on these websites that I'm highlighting here. So of course, you can also get DHS data for a lot of other countries as well, but you need to register for that country so that you can download the data. For this, at least if you're following along the video right now, you can go to this website and download it freely without the registration. And we will be using what we call the FUBUS history data. So on this website, it will be under this birth record section. And we're going to be using this datasets, which is a .dta file. Okay. So we're going to be using this package called race-data13 to load the data into our workspace. So if you download the DHS model dataset from the website, it will give you a zip file that has a very complicated file name starting with the Z. And I just unzip it and use this line of codes. and it will read this data frame into R. This is a relatively large data frame, so it will take a minute, and now we're here, and we can see that this data has a lot of observations with 971 variables. A lot of them we're not going to be using for our purposes in this lecture. So the first thing that we will do in pre-processing the data is to just subset the data by its region. So for a lot of the DHS data, especially the more recent ones, this variable called V139 is a code for the region variable in the data. So in order to see what it looks like, you can do this simple command called table. So you can do table data $V139. And you'll see that it gives you a table of the different values. So for this particular model data set, it has region 1, 2, 3, 4, and something else. So for this, of course, this is simulated data, so we're not actually throwing away any real information. So for this simulation example, I'm just going to use those 4 regions. So I'm going to subset our data and use those region 1, 2, 3, 4. Okay. And now you can also look at what the data looks like. For example, using this hat command, it gives you the first couple rows, and I'm specifying to look at the first 10 columns in this case. So the first thing you will notice that in DHS data, at least, the column names are not really that informative. You need to understand what their code, those V005, 006, so those numbers encodes. So you can find this information on the DHS recode manual, and again, it's on the DHS website, or you can just Google it. So some of the things that we will be using for our lecture are listed here. So we're going to need some of the variables specifying survey designs. For example, what strata a observation corresponds to. So it's typically the V023. And then we need the cluster ID, V001, household ID, survey weights, just to specify the survey designs when we're trying to get design-based estimates. A few things that we also need in order to understand the birth history, when the birth happened, when the death happens, and what are the ages of the children. You need the date of interview, the date of child's birth, the age of death of child in months, and also the indicator of whether or not the child died in that particular month. Okay, so those information you can get from the recode manual, and for some of the earlier DHS, you might need to look for some early recode manuals, which might be a little bit different than what's showing up here. So one thing that's, if you go into the data set and look at all of those dates variables, one thing you might notice is that they're not really in a very easy to interpret date formats. They're all numerical values, which are basically what is called the central month code, or CMC formats. So what it does is basically it's calculating the number of months since the beginning of 1900s. So there's one particular thing that might be of caution for a lot of users, that if you're working with a DHS dataset that's not using our common calendar, for example, Ethiopian calendar is off by 92 months, for example, you might need to adjust that particular CMC codes. And in some of the functions within the summer package, we actually have arguments to do that. So there's argument called cmc.adjust, and in the getBirth function, which I'll show you in a minute. And if you have questions for any of those arguments, you can always just do $getBirth, and it will give you a full documentation of how to use those arguments. Okay, so this is the basics of the data structures in a typical DHS survey. Of course, if you're using other type of surveys, you might need to change some of those variables and how they're coded. But essentially, those are the information that we will need in terms of calculating under-file mortality. So as we have discussed in the lecture series, that a lot of the DHS, or actually most of the DHS, uses something called a stratified cluster sampling design. So basically, the country is firstly partitioned into a set of strata, typically province or the admin 1 area, by crossed by urban rural. And then within each strata, you will have the clusters of V001. And then once the clusters are sampled within each cluster, you then sample the household V002, and then the individuals in the households are selected for interview. So in order to calculate design-based estimates, you need to know exactly what the sampling design is. And for the DHS data, it basically means you need to know what those variables are. So as we have discussed in the lecture, the first thing we're going to be doing in order to calculate under-5 mortality rates using what's called a discrete survival model, the first thing you need to do is to obtain your data, to transform your data into the person-month formats so that each child may contribute up to 60 person-months if you're working with a under-5 mortality rates. So in order to do that, we will need this function called getBus from the summer package. So we'll use, so this is how we're going to transform the data into person months. So we use this getBus function and need to specify the data, which is the food birth history data that we just downloaded from the DHS model datasets. You need to specify the survey year. And in this particular case, I have examined, and you can actually use this 2 lines of code to make sure that these model data sets actually correspond to a survey that's being implemented in the year 2015. And then you need to specify strata. So in this particular case, V023. And you need to specify the actual time of birth, the age of the kids, and then whether or not the child is alive. So those things, all of the things we have, and also, of course, the time of interview. So basically all those things we have discussed before that will be useful. So another useful functionality here is that you can specify which variables you want to save. So as you can probably see from here, there are a whole bunch of variables that are not that relevant to our analysis at this point. So I'm just going to delete those columns and just save the ones listed here. Okay. So again, remember in the lecture we have discussed this already, that we want to divide the person months into different age groups. So starting from the first month, so 0 to 1, and then 1 to 12, so basically 1 to 11, so not including 12, and then other age, and then 12 months age groups afterwards. So basically we want to know for each of the person months which age group it belongs to. And that is specified in this months.cut arguments. So it basically specifies that there are 8 cuts, and what those there are 6 cuts, and what those 6 cuts are. And another thing that will be used later is whether or not is which year or which periods a particular person month correspond to. So in this analysis, I will use years starting from 1980 to 2020, and I will use 5-year periods. So if you just evaluate this part of the arguments, it gives you 1980, 85, 90, all the way to 2020. So basically, I'm going to have one variable attached to the outputs that says which 5-year periods this person month belongs to. So now I'm going to run this line of codes. It will take a few seconds. And now it's done. We can see that we have, for each line, for each row of your data, instead of it being a record, now it is a person month. So basically, a child, if it survived the first 5 years of life, it will contribute to 60 observations in these data sets. And then it has the other things we specified, which age group it belongs to, the time periods, the strata, and it also have the variables that we saved, such as V139, which is the regions. Okay. Now, once we have prepared our data into person month formats, we can get our direct estimates by fitting this discrete survival model that I discussed in the lecture before. So in order to do that, we have a function that's called getDirect. So we need one more thing as the input of this function, which is what are the time periods that we're using in this analysis. So if you look at the years, this R was created in this birth data frame, so this time variable. So you have 80 to 84 up to 2015 to 2019. Okay. So now, since I'm going to be using these years in multiple occasions later, I'm just going to create this variable called years. And then I'm going to use this getDirect function, again from the summer package. I need to specify the present month file, so that's birth. And then I need to specify this vector, which corresponds to an ordered list of the years. And then, of course, since we want to calculate region-specific and region and time-specific estimates of undefined mortality, I need to specify which variable gives you the information about region. So this region gives you specifies that. So I need to specify V139, and then need to specify the time variable, which is time, is here. And then in order to get the survey design correct, I need to specify cluster variable as well. So this will allow the program internally to know how do we actually use how do we actually call the survey package to get the correct estimates in fitting the binomial model inside. And then we need a variable for the age, and then a variable for the survey weights as well in order to get the correct survey design. Okay, so now I run this line of codes, which will take a little bit longer time. But by the end of it, we will be having a set of direct estimates or survey-weighted estimates for undefined mortality rates, and a bunch of other things, including the 95% confidence intervals, again, design-based confidence intervals, the logically transformed version of the undefined mortality rates, and its variances and precisions as well, which will be helpful for our future use when we want to smooth those direct estimates. Okay, so now this part of line has been evaluated. I can look at the direct estimates. I'm going to just enlarge it a little bit. So at the beginning of the direct estimates, you have all the national estimates of undefined mortality rates. So you can see the region variable here is all, so it corresponds to the national estimates. And you have the means, the lower and the upper 95% confidence intervals, the logit of the means, and the variance of the logit and the precisions of the logits. And of course, in this case, we only have one survey, so we don't have another survey variable. And as we will later demonstrate, with multiple surveys, we can use another function that's very similar to this, and it will loop through each of those surveys and calculate the direct estimates for each of the surveys. So you can also look at the last few rows of the direct objects. So this gives you the region-specific estimates. So in this case, region 4 in year 90 to 94, and then the estimates and confidence intervals and a lot of other things. Okay, so this is basically how we can calculate direct estimates of undefined mortality rates using the summer package. So the final thing before we wrap up this lecture is how do we visually check those numbers. So of course you can just look at those numbers from this big data frame, but it's not really that informative or easy to read. So the first thing that we're going to be trying to do is to draw a line plot, so that for each region and the national estimates, we're going to draw a line plot over the years of the undefined mortality rates or the mean variables here. So the first thing that we do is we turn this the years column, so that's direct $ years. I'm going to turn this column into a vector, so that when we plot, we know which years come after which, because right now it is a character variable that's not really, internally the program R does not really recognize what are the orders of those years. So I'm going to use this to turn this into a vector so that the ordering is enforced. And then I'm going to use ggplot to draw our first visualization. So as I said before, it works by specifying, in the simplest case, the three different things. So I'm going to call the ggplot function. I'm going to specify data, which is a direct estimate. I'm going to specify the aesthetic mapping, so which variable goes to what. So I'm going to say years goes to the x-axis, so that's the x equals years. Mean goes to the y-axis, and the color are coded by the region variable. And since we're doing the line plots, I need to tell the program which records correspond to the same line. So I'm going to specify with this group aesthetics, and then I'm going to specify our object, which is geom_line. And if you just run this line of codes, and it creates this object called G, which is our visualization. And you can see what it looks like by just typing G. And then it creates this line plots. So this is a little bit better than looking at the raw numbers, but again, it's really not that informative, and they overlap a lot. So one other thing that we really haven't plotted on this figure is the confidence intervals. So one way you can do that is by specifying this geom_error bar. So again, remember that we already have a visualization, so now we only need to add on top of it another part, or another geometric object, which is error bars. And in this case, I also add points so that I can more easily see where those points lie on this line. So again, now I add the error bars by specifying the mean, the max values. And you can see that they overlap a lot. So again, this is not great. So what I'm going to do next is by specify positions. So in this case, I'm going to use this one line of code to tell R that I want them to dodge each other. So they don't exactly overlap. Although they have exactly the same x value, I want them to shift around a little bit so they don't overlap. So I'm going to create this POS variable, and I'm going to add that to each of those calls. So when I'm drawing the line, I'm telling the position to be dodging one another. When I'm drawing the points, I'm going to tell the position to dodge as well, and then I'm going to draw in the error bars. I'm going to do the same thing. So the rest of this code, although it takes 3 lines, is really what we have already looked at before. So now with this line of codes, we can again draw this visualization. So you can see that they're now dodging each other, and you can kind of see them separating from each other. But again, this is probably still not good enough, because even though they're not exactly overlapping, it's really hard to tell which line goes to what once you have a lot of the lines that are crowded in the same place. So here, what I will do is to make it even a little bit more complicated. So again, I specify the data, the aesthetic mappings, I specify the lines. Now, instead of the error bars, I will do something called ribbon, which is something really similar, but as you will see, it creates a different geometric object. And now I'm going to use this facet wrap function to tell the program that I'm going to try to draw this for using different panels, and the panels are specified by the region variable. So if you try to do that, what it will give you is basically this. So now you have specified in your visualization so that you're splitting your plots into 5 different facets or 5 different panels, and each of them correspond to one region. And of course, the first one corresponds to the national estimates, because this says all here. And then you can add on top of it different other things as well, such as the points, the different themes. And if you can see here that the x-axis are kind of scattered together, so you can make them rotate. So now you get something that looks much more clean, and perhaps up to your subjective view, at least to me, it seems much prettier than what we start with. Okay, so again, this is still a relatively simple plot, but there are a lot of different themes that you can customize if you want to make your plot your own. You can even make annotations on those figures so that you can draw an arrow that's pointing towards one particular data points and highlight some things as well. Okay, so this is the end of our line plot adventure here. So now we're going to move on to how do we draw the maps, and that will be our last example of this session. So as we have seen before, we have loaded a map from the DHS websites, the shapefile that corresponds to the Kenya geography. For this example, since we only have 4 regions and Kenya has 8 regions in that map that we have loaded before, I'm going to use a demo map. This is a data that's already loaded into the summer package. So I'm going to take out the spatial data polygon file, assign it to geo, and I'm going to rename the regions to be region 1 to 4. And again, you can do the simple plot called plot geo, and gives you this demo map. And you might already recognize this is a map of Uganda, but for this visualization, we'll just rename those to be region 1 to 4, and then try to see how we can combine the data with the map, so that when you have an actual map and prevalence estimates, you can easily do that as well. So the function that we'll be using is this function called map_plots. So again, this is in the summer package, and what it does, it basically takes your data. So data equals direct, which is the direct estimates that we just calculated before. And then you need to specify the geo arguments, which is the map. And then, of course, you need to tell the program which variable corresponds to region in the data. So in the data frame, it is called region, and which variable correspond to regions in this map. And in this particular polygon file, this is called reg name, reg name. And then you need to specify which variables you want to plot. So the way I'm doing here is I'm specifying the values I'm plotting is called mean, and I want to subset my plots by a variable that's called years. And this data frame that we're inputting here is what people call it a long data frame instead of a wide data frame, because each of those years are not organized one column after another, but they're all organized into row by row. So this is called a long data frame. So I'm going to use this map_plot function to create a map. So it will take a minute to show up here. So as you see here, we have successfully combined the data sets with these maps. So again, although the region names are randomly selected, just as an illustration, so as long as the region names match each other, you can plot them using the map plots, and it's divided by each of those years. And the value we're plotting here, as you can see from the color legends, is the direct estimates, or the mean column, as we have already created. So there are also a bunch of other options in the map_plot functions that you can specify. For example, for a lot of the applications child mortality, you might want to rescale it to the mortality rates to be the number of deaths per 1,000 live births. There are options to do that, and there are also options to change the legends as well. So if you're interested in that, and we'll actually see some of those in later lectures as well, you can find the documentation by just typing $map_plots as before. Okay, so the last visualization I'm going to show you is something called hash plots. So again, as we have discussed in the lecture, that plotting things on the map is great, but you don't get to see the uncertainties of those estimates. So there is a function in the summer package that's called hash plots. So basically what it does is that it asks you to give two additional arguments, the lower and the upper, which corresponds to the confidence intervals or credibility intervals or any kind of uncertainty bounds. And then internally, it will calculate the width of those uncertainties. so the width of those intervals, and it will translate into how much hatching it performs on each of those areas. So if you make this look a little bit larger, as I'm showing up here, so there is instead of just the colors, which corresponds again to the direct estimates, the mean columns, there's also a legend that specifies uncertainty. So you can see that some of the areas have very heavy uncertainties, have very large uncertainties because it has very heavy hatchings. So the narrower those lines are, it means the basically heavier hatching or larger uncertainty, or the wider uncertainty bounds. So in this particular case, you can see at least here, although this is simulated data set, it does show that in the earlier periods, so this is 1980 to 84, you have much denser hatchings or much larger uncertainties. And as you move closer and closer to the present days, at some of those later plots, you will see the uncertainty bounds to be much narrower, or the hatchings to be much wider. And you can read off the uncertainties from the legends here as well. Okay, so this is basically what we will demonstrate in this session. And again, just as a reminder, hopefully by this point, if you haven't used R before, you have already seen some of the things that we can do in R. And again, we have demonstrated how do we actually calculate direct estimates and how to visualize the direct estimates with a line plot or on a map. So in the next few lectures, we will work with a little bit more informative data rather than the simulated data sets. And then we will discuss a lot more about how do we make other diagnostic plots and how do we interpret the results. So again, at the end, if you want to look for any help or documentations, it's always easy to just write this question mark followed by the functions. And that will give you the help files. And we'll also, for a lot of the functions in the summer package, we'll also demonstrate and use in future lectures, so you might get more chance to see how it works in real actions as well. Okay, so with that, I will conclude this first lecture on Introduction to R. And remember that on the PDF file, the slides here, that you have, there are a lot of additional resources if you want to learn R and do a lot of other things with R and for other tasks as well. Okay. And that's it for this lecture. Thank you.